morning to everyone. Myself, Dr. A. Swamy Naidu, PhD in extraction of marble metal, senior-most chemistry lecturer, CSIR NET qualified, AP Telangana SLET also qualified. Today, we are discussing about the chemical bonding topic. In chemical bonding, the main topic is VSEPR theory. VSEPR theory means the valency shell electron pair repulsion theory. So, valency shell, if you take any atom, number of shells are there. The last shell is valency shell. The chemical properties or chemical reactions and geometry of the molecule depends on valency shell electrons. In valency shell, if you take any molecule, electron pairs are there. In electron pairs are two types, lone pairs and bond pairs. Lone pairs and bond pairs are called electron pairs. So, based on these bond pairs and lone pairs, the shape of the molecule be predicted. And second topic is applications of VSEPR theory, and third one is geometry and shape of the molecules. So, these are the topics. Generally, the shape of the molecules depending upon the arrangement of electron pairs between all the electron pairs present in the valency shell of central atom. Suppose if you take water molecule in H2O, oxygen atom as a central atom. Oxygen atom is a central atom. Hydrogens are bonded atoms. Two hydrogens are bond atoms. These are bond pair of electrons. These two are lone pair of electrons. Here, two lone pairs and two bond pairs present on oxygen atom. But the lone pair of electrons belongs to only central atom. But the bond pair of electrons belongs to both central atom and bond atom. Right. These repulsions between the lone pairs and bond pairs. These are the lone pairs. These are the bond pairs. The shape of the molecule determined by the arrangement of the repulsions between the electron pairs present in the valency shell of central atom. The geometry of the molecule and shape of the molecule depends on the lone pairs. Repulsions between the bond pairs and lone pairs, lone pairs and lone pairs, and lone pairs and bond pairs. Generally, lone pairs occupies the more space on central atom. Lone pairs occupies the more space on central atom than the bond pairs, since the lone pairs is attracted by the one nucleus while the bond pairs attracted to the two nucleus. Suppose if we take ammonia molecule. In ammonia molecule, central atom is nitrogen. So, nitrogen has one lone pair and three bond pairs. The shared pair or lone pairs belongs to both nitrogen and hydrogen, but the lone pairs belongs to only nitrogen only. So, lone pairs occupies the more space because lone pairs belongs to only nitrogen here, but the bond pair of electrons belongs to both nitrogen and hydrogen, two nuclei, but the lone pairs belongs to only one nuclei, that is nitrogen, here ammonia. But the shared pair of electrons or bond pair of electrons belongs to both nitrogen and hydrogen, both nuclei. And next one, if the central atom contains only bond pairs, suppose if you take any molecule, the central atom has only bond pairs, the shape of the molecule and angle will be according to the expected lines. Suppose if you take methane molecule, carbon atom is a central atom. In methane molecule, number of electron pairs equals to 4. Here bond pairs equals to 4 and lone pairs equals to 0. So electron pairs nothing but bond pairs and lone pairs. Here totally 4 plus 0, 4 electron pairs. In the case of methane molecule, there is no lone pairs, only bond pairs. So what is the geometry of the methane molecule? Tetrahedral. So tetrahedral geometry. Suppose if you take carbon, act as a central atom, out of 4 bonds, tetra means 4, out of 4, 2 bonds in plane, out of 4 bonds, 2 bonds in plane, one is front of the plane, so another one is back of the plane. The geometry of the molecule is tetrahedral. So these are the expected lines. But in the case of ammonia, electron pairs are 4, bond pairs equals to 3, but lone pairs equal to 1, the total electron pairs equals to 4. But we are expecting geometry is tetrahedral, but here one lone pair is there, so the geometry is pyramidal geometry. Suppose if the molecule central atom having only bond pair of electrons, the geometry is expected geometry is tetrahedral. Here 4 bond pairs. Out of 4 electron pairs, 4 bond pairs and 0 lone pairs. But in the case of ammonia, electron pairs are 4, but bond pairs equals 3, but lone pair equal to 1. One lone pair is present in nitrogen. So based on the repulsions between the lone pairs and bond pairs, the shape or geometry of the molecule is completely different. The shape of the molecule is what? Pyramidal geometry. Pyramidal. And next one. If the central atom contains lone pairs along with the bond pairs, then the shape of the molecule is deviated from your expected lines like ammonia. Ammonia is a pyramidal geometry, but methane molecule is tetrahedral geometry. The order of repulsions between the lone pairs, electron pairs, first one lone pairs is greater than, lone pairs bond pairs is greater than bond pair. The main reason is lone pairs occupies the more space on central atom. That's why lone pair repulsions are more when compared to lone pair and bond pair. Suppose if you take NH3 molecule, 1 lone pair and 3 bond pairs are present. This is lone pair. These are bond pairs. How many bond pairs here? 3 bond pairs. In this case, this is bond pair, this is bond pair. The repulsion between these repulsions are bond pair repulsions. Here also bond pair repulsions. Here, this is the lone pair, this is the bond pair. These repulsions are lone pair repulsions. Here also lone pair repulsions. Here, 2 different types of repulsions are observed. One is bond pair, another one is lone pair. So, here lone pair bond pair repulsions are greater than bond pair repulsions. The main reason is the lone pairs belongs to only central atom nitrogen only. So, lone pairs occupies the more space on nitrogen, but the shared pair of electrons or bond pair of electrons belongs to both central atom and bond atom. Here the sharing of electron pairs, but the lone pairs only belongs to central atom. That's why lone pair repulsions, lone pair bond pair repulsions is greater than bond pair repulsions. The bond angle also deviated. In tetrahedral, the bond angle is nearly 109 degrees 28 minutes in the case of methane, but in this case only because of the repulsions the bond angle will be deviated near 107 degrees. Bond angle means the angle between any two bond pairs in molecule, the angle between any two bond pairs. This is the bond angle. Bond angle is 107 degrees, but in the case of methane 109 degrees 28 minutes, but in the case of ammonia the bond angle is 107 because of the only reason lone pair bond pair repulsions is greater than bond pair repulsions. So finally lone pair repulsions is greater than lone pair and bond pair repulsions. The order of repulsions between different bonds is triple bond is greater than double bond is greater than single bond, because in triple bond 3 bond pairs are present, in double bond only 2 bond pairs, in single bond only 1 bond pair. Here the number of electrons are more, here 3 bonds 6 electrons, here 2 bonds 4 electrons, here 1 bond 2 electrons. So number of electrons increases, repulsions also increases. So triple bond repulsions is greater than, double bond repulsions is greater than single bond. Next, the applications of the molecule. It's very important. Please listen carefully. So applications of VSEPR theory, valence shell, electron pair, repulsion theory. Right. This is the first application. Type of molecule, geometry of the molecule, shape of the molecule, and how many lone pairs and bond pairs present on the central atom, and examples. The type of molecule is AX2 type, AX2 or AB2. AB2 means here A acts as a central atom, B is a bond atom. How many bonds here? 2 bonds, 2 bond pairs. A is a central atom, B is the bond atom, 2 bonds, adjust in linear geometry, the angle is 180 degrees. The geometry of the molecule is what? Linear geometry. Shape of the molecule also linear because here only 2 bond pairs are present. Suppose if you take BeCl2 molecule, barium chloride. In beryllium chloride, beryllium acts as a central atom. So beryllium belongs to second A group element. Their valence shell has 2 electrons, 1, 2 right like this. Here chlorine atoms, 2 chlorine atoms act as a bond atoms. Bonded atoms. Suppose if you take hydrogen act as a bond atom, it forms single bond. Halogens, fluorine, chlorine, bromine, iodine, these are act as a bond atoms, form single bond. Suppose if you take oxygen family, forms double bond. If you take nitrogen family, forms triple bond. Right, here beryllium acts as a central atom. So beryllium is belongs to second group element. So 2 electrons in valence shell. So 1, 2. But here bond atom is chlorine atoms. Here 2 chlorines are present. So 2 bond pairs. This is electron. This electron belongs to beryllium. And this electron belongs to chlorine. 1 bond pair. Second electron of beryllium. This electron of the chlorine. Bond pair. How many bond pairs here? 2 bond pairs plus 0 lone pairs. There is no electrons are remaining on beryllium atom. There is no lone pairs. So totally how many electron pairs? 2 electron pairs. 2 bond pairs, 0 lone pairs. The expected geometry is linear. So beryllium chloride is linear geometry. Here this is beryllium atom. This is beryllium atom. These are chlorine atoms. These two are bond pairs. The angle between these molecules, these 2 bond pairs is 180 degrees. This is linear geometry. Linear geometry. The next one. Next application. The type of molecule is AX3 type or AB3 type. Here number of bond pairs are 3. The geometry is trigonal planar. Trigonal planar geometry, because here 3 bond pairs are present. How many lone pairs and bond pairs? Total electron pairs are here 3 electron pairs. In 2 cases, the first case is case number 1. The first case is out of 3 electron pairs, 3 bond pairs plus 0 lone pair. Total electron pairs 3 electron pairs. This is one case. And another case is out of 3 electron pairs, 2 bond pairs and 1 lone pair. Total 3 electron pairs. This is first case. This is second case. So 3 electron pairs. Example of the molecule is beryllium or boron trichloride, BCl3. Boron trichloride, boron trifluoride. If you take any halogen, boron trihalides, trigonal planar geometry. This is the trigonal planar geometry. If you take boron is belongs to third A group element, 3 electrons in valence shell. 3 electrons in valence shell. Chlorine forms single bond because it is halogen. Halogens or hydrogens form single bond. So 3 single electrons of boron forms 3 bond pairs. So 3 bond pairs, 0 lone pair. There is no electrons present on boron atom after formation of 3 bonds. In beryllium chloride, beryllium atom acts as a central atom. In boron trichloride, boron atom acts as central atom boron, and chlorines are bond atoms. Here 3 chlorines. The angle between the any 2 bond pairs is 120 degrees. 120 degrees. Total 360 degrees by 3, 120. The angle between 2 bond pairs in boron trichloride is 120 degrees. And next one, case number 2. Here 2 bond pairs and 1 lone pair. The total electron pairs are 3 electron pairs. Example is SO2 molecule. The example is what? SO2 molecule, sulfur dioxide. In sulfur dioxide, sulfur atom acts as a central atom. Sulfur atom acts as central atom. Sulfur atom which belongs to 6A group elements. 6A group elements, so valence shell has 6 electrons. Sulfur act as the central atom. Sulfur belongs to 6A group element, 6 electrons in valence shell. But here bond atom is oxygen. Oxygen forms double bond, oxygen family, oxygen, sulfur, selenium, polonium. In oxygen family forms double bond. Double bond means 2 electrons are required. So first 2 electrons of sulfur, one oxygen form double bond, and second oxygen double bond. This is lone pair. So how many bond pairs here? 2 bond pairs and 1 lone pair. This is lone pair. 1 lone pair. Total electron pairs, 3 electron pairs. The geometry of the expected geometry of the molecule is trigonal planar, but the actual shape is V shape or angular shape. This is V shape or angular shape. This is the sulfur atom. These are the oxygen. These are 2 oxygens. Double bond, and 1 lone pair. 1 lone pair. This is bent shape or angular shape. Bent shape or angular shape or V shape. V shape. Okay. This is AB3 type molecule. This is AB3. This is case number 1. And another one is AB2E type. This is AB2E type. E means here A central atom has 2 bond pairs, and 1 lone pair. E indicates lone pair. These are the second applications. Next one. Next type of molecule is AB4 type. AB4 type. AB4 type here 4 bond pairs, 4 electron pairs. 4 electron pairs. Out of 4 electron pairs, case number 1, 4 bond pairs plus 0 lone pairs, one case, and second case is 3 bond pairs plus 1 lone pair, this is second case, and third case is 2 bond pairs plus 2 lone pairs. 3 cases are there. The first one, this is AB4 type, expected geometry is tetrahedral. This is AB3E type. This is AB2E2 type. Here example is CH4. Here example is ammonia. Here water molecule and H2S. This is PH3, CCl4, SiCl4. These are the examples. Electron pairs, out of 4 electron pairs, 4 bond pairs, 0 lone pairs. The expected geometry is tetrahedral geometry. This is tetrahedral. Tetrahedral. Tetra means 4. 4 hydrals. Okay. So out of 4 bonds, 2 bonds in plane. These 2 bonds in plane. This is front of the plane. This is front of the plane. Out of 4, 2 bonds in plane. These 2 are plane. This bond is front of the plane and this bond is back of the plane. Out of 4, these 2 are in plane bonds. This is front of the bond. This is back of the plane. Back bond, front bond. 2 bonds in plane. Totally 4. 4 bonds and 4 hydral angles. Tetrahedral. the bond angle between any two bond pairs nearly 109 degrees. Suppose if you take methane molecule CH4, here carbon atom acts as a central atom. Carbon belongs to 4th group element. So 4 electrons in valence shell. Hydrogen forms single bond. So 4 bond pairs plus 0 lone pairs. So 4 electron pairs. The geometry is tetrahedral geometry. This is the case number 1. Case number 2. Out of 4 electron pairs, 3 bond pairs and 1 lone pair. The geometry is, expected geometry is tetrahedral, but because of the 1 lone pair, the actual shape of the molecule is pyramidal. Pyramidal geometry. Suppose if we take PH3 or NH3, any 5th group element hydrates, NH3. Okay. Here nitrogen is central atom, nitrogen belongs to 5th group element. So 5 electrons in valence shell. Here hydrogen forms single bond. 3 hydrogens forms 3 single bonds. This is lone pair. 1 lone pair and 3 bond pairs. 3 bond pairs plus 1 lone pair, total 4 electron pairs. So 4 electron pairs, expected geometry is tetrahedral, but 1 lone pair is there. This is lone pair. 1 lone pair. Nitrogen atom has 1 lone pair. These are bond pairs. These 3 are hydrogens. 3 are hydrogens. Pyramidal geometry. Here the bond angle is 107 degrees. The main reason is here lone pair bond pair repulsions is greater than bond pair repulsions. Because of these repulsions, the bond angle will be decreases from 109 to 107. Bond angle is decreases. And next case is AB2E2 type. In this case, 2 bond pairs and 2 lone pairs. Example is water molecule. In water molecule, oxygen atom acts as a central atom. Oxygen belongs to 6A group element. So here 6 valence electrons present in oxygen. Here 2 hydrogen atoms are bonded atoms. Hydrogen forms single bond. These are bond pairs and these 2 are lone pairs. So here 2 bond pairs plus 2 lone pairs, total electron pairs, 4 electron pairs, but the expected geometry is tetrahedral. Expected geometry is tetrahedral, but the actual shape is V shape or angular shape. Here 2 lone pairs, 2 bond pairs and 2 lone pairs. Here we observe the bond pair repulsions. This is lone pair repulsions. Here lone pair repulsions. Here lone pair repulsions. So lone pair repulsions is greater than lone pair repulsions is greater than lone pair repulsions is greater than bond pair repulsions. Here 3 types of repulsions observed in this case. In the case of water molecule, 3 types of repulsions are observed. Lone pair repulsions on oxygen, lone pair repulsions, oxygen between the hydrogen, and bond pair repulsions, 2 bond pairs, hydrogens, and lone pair repulsions. So lone pair repulsions are very greater than when compared to lone pair and bond pair repulsions. The bond angle is 104 degrees. Here 109 degrees, only bond pairs. Here 1 lone pair is there. The bond angle is 107. Here 2 lone pairs are there. So bond angle is 104, slowly deviated. Bond angle is decreases because of lone pair repulsions are very high repulsions when compared to lone pair bond pair and bond pair repulsions. This case is very, very important. And next one. Next type of molecule here AB5 is central. How many bond pairs here? 5 bond pairs. So electron pairs are 5. The first case is bond pairs, 5 bond pairs. So 5 bond pairs plus 0 lone pairs. This is the first case. And case number 2, 4 bond pairs plus 2 lone pairs. And case number 3, 3 bond pairs plus 2 lone pairs. And case number 4, 2 bond pairs plus 3 lone pairs. These are the cases. For bond pairs, this is AB5 type, this is AB4 E type, this is AB3 E2 type, this is AB2 E3 type. Expected geometry of the molecule is trigonal bipyramidal. Trigonal bipyramidal geometry. Trigonal, 3 bonds present on one plane. 3 bonds present in one plane. 2 bonds. One bond is above the plane and another bond is below the plane. See, this is the trigonal bipyramidal geometry. These 3 bonds, 1, 2, 3, these 3 bonds in plane. This is trigonal. The angle between these 2 bond pairs 120 degrees. These are trigonal. These 3 bonds are in plane. And one is above the plane. This bond is above the plane. This bond is below the plane. These are axial bonds. These are axial bonds. These 3 are equatorial bonds. These are axial bonds. These are equatorial bonds. In trigonal bipyramidal, these 3 bonds are equatorial. These 2 are axial. The angle between equatorial and axial is, these 2 bonds are perpendicular. So bond angle is 90 degrees. Here also 90 degrees. The axial bond, the bond angle between axial is 180 degrees. The geometry is what? This is trigonal bipyramidal. In this case, 5 bond pairs plus 0 lone pairs, 5 electron pairs. This is AB5 type molecule. And in this case, 4 bond pairs plus 1 lone pair, total 5 electron pairs. 4 bond pairs, 1 lone pair, totally 5 electron pairs. This is seesaw shape. This is what? Seesaw shape. Here 3 bond pairs plus 2 lone pairs, total 5 electron pairs. This geometry is T shape. Generally, Expected geometry is trigonal bipyramidal, but actual shape is, this is shisha shape, this is T shape. And finally in this case 2 bond pairs plus 3 lone pairs, 5 electron pairs, the geometry is linear geometry. Okay. Now, so what are the examples? The first example is phosphorus pentachloride PCl5. Here SF4, ClF3, here XCF2, right. In PCl5, phosphorus is a 5th group element, 5 electrons in valence shell. Chlorine, so 5 chlorines forms 5 bond pairs, so 5 bond pairs plus 0 lone pairs. Here phosphorus is a central atom, remaining chlorines are bonded. This is the phosphorus, these are 5 chlorines, and this is the phosphorus. Phosphorus is a central atom. So this is shisha shape. Example is SF4. Here sulfur is 6th group element, 6 electrons in valence shell. So fluorine forms single bond, 4 bond pairs and 1 lone pair. 4 bond pairs and 1 lone pair. Because of the lone pair bond pair repulsions, the shape or geometry of the molecule is deviated. Original geometry is trigonal bipyramidal, but the actual shape is shisha shape because of the 1 lone pair present on central atom. Here central atom is sulfur, and how many fluorines? 4 fluorines. 1, 2, 3, 4. This lone pair present on equatorial position only. This is very, very important. Here equatorial and axial, 2 positions are there, but the lone pair present on only equatorial because of the minimum repulsions, maximum stable. The shisha geometry, the lone pair present on only equatorial but not axial. This is very, very important. The main reason is lone pairs in equatorial positions, the minimum repulsions, maximum stable. And next case, 3 bond pairs, 2 lone pairs, interhalogen compounds, ClF3, chlorine trifluoride. Both are halogens. One halogen mixed with another halogen. This is example of interhalogen compound AX3 type. So here chlorine is a 7th group element, 7 electrons in valence shell. Fluorine act as a bonded atom. Here chlorine act as a central atom, fluorine F act as a bond atoms. So fluorine forms single bond. Here 3 bonds and 2 lone pair of electrons. These lone pair of electrons also arranged in equatorial position only but not axial. Okay, so 2 equatorial positions. This is one lone pair, this is another lone pair. This is chlorine atom, these are fluorine atoms. These are fluorines. This is T shape. But the actual geometry is trigonal bipyramidal, but because of the 2 lone pairs, these lone pairs arranged on the equatorial positions, the shape of the molecule is T shape. And next case, out of 5 electron pairs, 2 bond pairs, 3 lone pairs. Suppose if we take xenon difluoride. Xenon is a inert gas, but except xenon, remaining all are inert, but xenon is reactive because of the large size. Xenon reacts with highly electronegative elements like fluorine and oxygen. Xenon forms xenon fluorides and xenon oxides and xenon oxyfluorides. In xenon fluoride XeF2, the geometry is linear geometry. Right. We take xenon 8, 2 fluorines. 2 fluorines forms 2 bonds, and here 3 lone pairs, 2 bond pairs and 3 lone pairs. Xenon is 0 group element, 8 electrons in the valence shell, 8 electrons, but here fluorine forms single bond, 2 bond pairs and 3 lone pairs. 2 bond pairs and 3 lone pairs, totally 5 electron pairs. The geometry is linear geometry. This is xenon, these two are fluorines. This is linear geometry. Okay, AB5 type, 5 electron pairs, 5 electron pairs out of 5, 5 bond pairs, 0 lone pairs. Geometry is trigonal bipyramidal. Next, 4 bond pairs, 1 lone pair. Geometry is shisha shape. And next, third case, 3 bond pairs, 2 lone pairs. Geometry is T shape. Example is ClF3. And last case is 2 bond pairs and 3 lone pairs, AB2 E3 type. XeF2 is example. So geometry is linear shape. And next one. Next, next type of molecule, next type is AB6, here 6 electron pairs, 6 electron pairs. Cases. Case number 1, AB6 all are bond pairs, 6 bond pairs plus 0 lone pairs, 6 electron pairs. This is the first case. And second case is AB5 E type. Here A is central atom, B 5 bond pairs, E indicates the lone pair, 5 bond pairs plus 1 lone pair, 6 electron pairs. This is second case. And next case is AB4 E2 type. So 4 bond pairs plus 2 lone pairs, totally 6 electron pairs. So these are the cases. Here the example is SF6. Example is SF6. Here the example is xenon oxy tetrafluoride XeOF4, and here the example is XeF4 xenon tetrafluoride. These are the examples. Okay. So coming to the AB6 type, case number 1, AB6 type, here 6 bond pairs plus 0 lone pairs, the total electron pairs 6 electron pairs. The geometry of the molecule is octahedral. Octahedral, but here only bond pair 6, but here the geometry of the molecule is octa. Generally oct means 8, but here bonds are 6. What is the difference between these two? What is the relation? Here the geometry is depends on not a bonds, faces. Oct means 8. 8 faces. In octahedral, 8 faces, but 6 bonds, but 8 faces. Above the plane, 4 bonds, 4 above the plane, 4, and below the plane, 4, totally 8 faces. That's why these geometry are called octahedral geometry. In octahedral, out of 6 electron pairs, 6 bonds, 4 bonds in plane, these 4 bonds in plane, these 4 in plane, this is square planar, right? These 4 are in plane. And the bond between these 2 bond pairs are 90 degrees. And above the plane 1 bond and below the plane 1 bond, totally 6 bonds. The geometry is octahedral. 4 bonds in above the plane and 4 faces below the plane. Below the plane 4 faces, above the plane 4 faces, totally 8 faces, but bonds are 6, but geometry completely based on faces, here 8 faces. Example is SF6. In SF6, sulfur atom acts as a central atom, which belongs to 6th group. So 6 electrons in valence shell. So fluorine forms single bond. So 6 bond pairs plus 0 lone pairs, totally 6 electron pairs. Out of 6 electron pairs, all 6 are bond pairs. The geometry is octahedral geometry. This is AB6 type molecule. And next case is AB5E type. AB5E type. AB5E type. Here 5 bond pairs plus 1 lone pair, total 6 electron pairs. 6 electron pairs, experimental geometry is octahedral, but actual shape is square pyramidal, because here 4 bonds in plane, 1 is above the plane. This is square pyramidal geometry. The example is xenon oxytetrafluoride. In xenon oxytetrafluoride, 4 fluorines are in plane and oxygen forms double bond above the plane. This is xenon oxytetrafluoride. In xenon oxytetrafluoride, xenon belongs to 0 group elements. So 8 electrons in valence shell. 8 electrons in valence shell. In 8, oxygen forms double bond, 2 electrons are required. Oxygen forms double bond, 2 electrons are required, but fluorine forms single bond. How many fluorines here? 4 fluorines. 4 electrons are required. This is lone pair. 1 lone pair, 5 bond pairs. These 5 are bond pairs and 1 lone pair below the plane, arranged in the below the plane. The geometry is what? Square pyramidal. Square pyramidal geometry. Square pyramidal. And next case, AB4E2 type. 4 bond pairs, 2 lone pairs. 4 bond pairs, these are arranged in the square planar shape. Example is xenon tetrafluoride, xenon 8 electrons in valence shell, 4 fluorines forms single bonds and 2 lone pairs. So 4 bond pairs, 2 lone pairs, totally 6 electron pairs. 6 electron pairs. Here xenon atom acts as a central atom and 4 fluorines. The geometry of the molecule is square planar and 2 lone pairs. These 2 are lone pairs arranged in the opposite side because of the minimum repulsions, maximum stable. So XCF4 is square planar geometry. Okay? Thank you. Thank you.